So the purpose of this talk is really to introduce the idea of the gravity method for imaging the subsurface, and especially taking gravity measurements from the air. And as just a quick summary of the contents, first of all, I'll introduce the gravity method with some simple examples. But then as we start to talk about the dynamic measurement, which is very much the airborne environment, we'll then move on to gravity gradiometry, which really is the key to measuring high accurate gravity fields from the air. Then I'll show a few examples of gravity gradiometry survey data. And then I'll move on to something perhaps a bit more relevant to this webinar series, which is talking a bit more about geothermal modeling and how that applies to gravity and gradiometry surveys. And then we'll have a look at some gravity data from Northern Ireland and do a simulation of that data as though we were acquiring an airborne survey and see how that compares to the land data. So we go straight into it then. So the basic concept of gravity exploration is really looking for differences in density in the Earth. Now, the typical application of this has been looking for sedimentary basins. And where you have a rift, and that has been filled with sedimentary deposits, what you have there is essentially a low density area surrounded by high density. And if you measure the gravity across this area, the gravity measured will decrease as you go over the lower sedimentary rocks. So this is a very simple example. Obviously, there's many more applications of gravity, but historically, the gravity method has been well used for finding sedimentary basins, and this has been in the hydrocarbon industry. Now, the majority of gravimeters work more or less on the same principle. It's a very simple principle, but very sensitive measurement. So in some ways, the physics is quite easy to understand, but it's the engineering which is very difficult because you're making a very, very sensitive measurement of a very small change in gravity as you move across the Earth. But the essential idea is you have a mass on a spring, and if the gravity changes, so if the gravity increases, that increases the weight of the mass, that increases the extension of the spring, and that is the basis of your measurement. You're measuring the extension change in the spring, and that gives you the recorded value of gravity. Now, here are these the land instruments that are used for land gravity surveys. On the left, you have a somewhat more traditional instrument, a Lacoste and Romberg instrument, and a slightly more modern version on the right there. But with a land gravity survey, essentially what you're doing is you're taking this instrument, this very sensitive instrument, and you're moving it from one place to another place on the Earth. And at each point, you're stopping, taking a measurement, writing it down, and then moving across to the next station. So it takes a very long time to build up a network of these gravity measurements. But over many decades, there has been a lot of land gravity measurements made, especially across the UK. There's quite a good coverage. And later on in this presentation, we'll be having a look at some of the data that's being collected in Northern Ireland. But the next challenge is really, how can you make these measurements in a dynamic environment? And when I say dynamic environment, I'm really talking about the airborne situation. So the advantage of an airborne survey, of course, is that you can cover much greater areas very quickly. And also, you don't have any access problems. The land surveys traditionally followed paths and roads where access was relatively easy. But that meant there were great areas which don't have any measurements, the places which are difficult to access. With an airborne survey, of course, you don't have that problem. You can cover lakes, you can cover forested areas, no problem at all. So there's a huge advantage in taking these measurements from an aircraft. Now, when it comes to gravity measurements, you're really restricted by what's known as the equivalence principle. This is Einstein's famous equivalence principle, which says that you can't distinguish between a change in gravity and a change in acceleration unless you have some external measurement. So what it means is that gravimeter, consisting of a mass on a spring, when the spring extends, you don't know whether that's a change in gravity or a change in acceleration. And of course, in an aircraft, the acceleration environment is very extreme. So what this means is that you have to have that external reference, and that comes from GPS, and that corrects the data and removes the acceleration term. Now, the problem here is that GPS is not that accurate for this type of measurement, and it means that the data needs to be filtered quite heavily. So it means that gravity measurements from an airborne system tend to be quite smooth. The filtering times, maybe 100 seconds, means that you lose the resolution in the data. The answer to this really is the airborne gravity gradiometer. And these have been around for a few decades now, probably getting on for 25 years, really, in the airborne environment. Now, the key to this system is that it takes two measurements of the gravity field, and it differences those measurements. And when you difference the measurements, the acceleration of the aircraft disappears, and now you end up with just the difference due to the change in gravity from one place to another. So this diagram on the left is an attempt to illustrate that, where the two red dots represent the points of measurement, and they're separated by maybe 10 or 20 centimeters, so quite a short distance. But the one at the bottom here, with it being closest to the source, the treasure, if you like, the thing that you're trying to measure the gravity from, that will have a slightly greater pull of gravity than the one which is a little bit further away. So when you difference those two measurements, you now end up with the change in gravity from one point to another point. And as I said before, the acceleration, which is the same at both of the points, cancels. So this really is the perfect situation for a dynamic measurement, because your vibrations of the aircraft disappears, and you're left with something that now only represents the gravity coming from the source of interest. So this slide really summarizes the services that we offer at Metatech. We're very much an exploration survey company, and we cover many different fields of exploration. And we focus mainly on gravity gradiometry in the airborne environment. But once you've got an aeroplane kitted out with some equipment, you try to take as many measurements as possible. So this is one of our aircraft, and this is the one we used for our sort of larger instrument known as the enhanced FDG, and that sits essentially at the center of gravity of the aircraft. That's the ideal position for a very sensitive inertial system. But at the back, we also take magnetic measurements using a magnetometer. And at the front of the aircraft, we take measurements of the topographic elevation using a LiDAR system. So we not only acquire the data, we also process the data and then do the various interpretation. And the interpretation ranges right from producing maps of the gravity fields and the magnetic fields and the topographic data from the LiDAR, all the way through to producing three-dimensional models and full interpretations of the subsurface geology. So to give a quick comparison of airborne gravity and airborne gradiometry, this image here in the middle is fairly typical of an airborne gravity survey, which is very good at picking out essentially things like sedimentary basins, things which have sizes of the order of 5 to 10 kilometers and bigger. But what you don't get from this type of survey data is very high resolution detail about the subsurface geology. Now, if you compare that to the airborne gradiometry situation, that picks up the sedimentary basin, of course, but it also picks up structures within the basin. So now you're getting a much higher resolution data set. And this is quite important for targeting exploration programs and combining the data with other data sets, for example, seismic data, and producing a full interpretation of the subsurface. So we can put some numbers on here that, based on the resolution of the data. It's all down to how much the data is filtered, really. So I mentioned before, gravity data is typically filtered with 100 seconds. Gradiometry data is filtered much less, in fact, generally less than 5 seconds. And this gives you resolutions of 150 meters for that gradiometry data. So you can see changes in the geology over a length scale of about 150 meters. And this compares to a few kilometers when it comes to airborne gravity data. So to give you an idea of how an airborne gravity gradiometry survey actually happens in terms of its operations, we would generally turn up at a nearby airport. That's the sort of mobilization phase of a project. There'll be maybe 2 or 3 days of calibrations where we calibrate various instruments. We run various tests on the instruments to make sure everything's working correctly. We do reconnaissance flights just to get an idea of the topography in the area to make sure there's no surprises or anything like that. And then we start doing a survey. And this is quite a small survey example here, just maybe 20 kilometers by 20 kilometers across. And from the airport, the aircraft will fly to the survey area, and then it will fly a series of lines. And typically, an airborne gravity gradiometry survey will collect between, let's say, 300 kilometers to up to 1,000 kilometers of data per flight. Not all of this data, of course, is within the survey perimeter. Some of that is run-ins and run-outs from there. And of course, there's the associated turns to do with that flight. So after a single flight, we might end up with data along lines neatly cropped to the area, as we see in this middle image. And then after a few more days of flying, we would have acquired the data over the entire area. So not only do we have the data acquired on these lines, which are fairly tightly spaced in this direction, but we also have lines in a perpendicular direction, and these are called the tie lines. And these really assist in the processing of the data to make sure that all the errors and drifts and any other situations can be properly accounted for and corrected for in the data. So here's a fairly simple, what we call a feasibility model. And we always do one of these before we start a survey to get an idea of the type of signals that we might be expecting during a survey. And we use these to plan also what line spacing the survey should be acquired at. Obviously, the tighter the line spacing, the higher the resolution the data, the more accurate the data will be. But of course, the tighter the line spacing, the more kilometers that are flown, and hence the greater the time scale of the project, and the knock-on effect, of course, of that is the higher the price. So we try to design our surveys to be optimal for the geology of interest. And here we see an example. This is really from a mining industry situation, where we're looking for kimberlite pipes. And for those of you that know about kimberlite geology, these are the situations where you tend to find diamonds. They're fairly small underground volcanoes, and as the volcanoes have erupted, they tend to bring up diamonds, and of course that is now the if you find the kimberlite pipe, you're more likely to find diamonds. So these become the areas of interest for diamond exploration. But in fact, they are also the ideal target for gravity gradiometry because they're fairly localized. They have a low density compared to their surroundings. So we expect to see the gravity dropping down as we fly over the kimberlite pipe. But they're fairly high frequency features, fairly short wavelengths, and therefore they lend themselves quite nicely to these gravity gradiometric surveys. So what we see here is a geological model. On the left, we have a few geological layers, and intruded into these layers, on the right, you can see these green kimberlite pipe volcanoes, and these are the targets of interest. So we've got a model here with a few different sizes and a few different depths of these kimberlite pipes. So what we do before we start a survey is we design a suitable flight plan. And this, you can see on the top of this diagram here, where we've got a spacing of flight lines with 100 meters and an associated spacing of perpendicular tie lines with 500-meter spacing. And then what we can do with this is simulate an airborne survey. So on the top here, you see the perfect response. So this is as though you've got perfect sampling. You know, the line spacing is essentially infinitesimally small. There's no acquisition pattern. It's perfect sampling. There's no noise in the data. You know, this is the actual perfect response from that model. And here you can see very clearly the kimberlite pipes, the signature of the kimberlite pipes in this gravity gradient map. So the blue colors here represent low values of gravity gradient, and the red colors represent the higher values. Now let's look at the simulation. In this case, we've simulated two different gravity gradiometer instruments, one known as the full tensor gradiometer and the other one known as the enhanced full tensor gradiometer. So the enhanced version is a later, a more up-to-date version of the full tensor gradiometer. It's much bigger, it's much more sensitive, and it's able to acquire very, very accurate data, even in high turbulent conditions. So with these feasibility models, not only are we able to plan what line spacing is suitable for a survey, we're also able to test what instruments is suitable for various surveys. So on the left-hand image here, you can see the results of the FDG simulation. And it does pick up quite clearly the larger kimberlite pipe signatures. And we see on the top right and the bottom left, these two signatures coming through quite clearly. But the smaller kimberlite pipes are somewhat lost in the noise in the data. And you wouldn't really be able to pick out some of these lows from what we can call false lows. And those false lows are really just manifestations of the noise in the data. When it comes to the more advanced FDG, the enhanced full tensor gradiometer, which has much lower noise in that system, now we can see that we see the kimberlite pipes much more clearly, and even the smaller ones are starting to come through with fairly high confidence. The other thing that happens with gradiometric surveys is that I mentioned before that these instruments are full tensor gradiometers. That means that not only are they measuring the gravity field in the vertical sense, but they're also measuring the gravity field in a three-dimensional sense. So they're measuring how the gravity changes in different directions. And this is very useful because it allows you to see how the gravity is changing away from the line at which you're acquiring the data. And this is nicely exampled by this survey, which we did, I think it was about maybe 10 years ago or something like that, where we were doing a survey for salt domes. And these, again, are quite similar geological features to the kimberlite pipes, in the sense that they have a low density surrounded by higher density sediment. So that means that they'll give a low in the gravity field. And also they're quite localized, so similar-ish sizes, bigger than the kimberlite pipes, but still relatively localized anomalies. And these salt bodies produce very nice maps in terms of their gravity field. And on the left here, we see what we can almost call the truth, in the sense that this really is what the gravity field looks like in this area of the world. And we can say that because this is a very tight line spacing, 150 meters. So that means the data is going to be very accurate. Now, if I only select lines from this survey, which are separated by 5 kilometers, we can see what the data would have looked like had this been a severely undersampled survey. So now we only have data along these much widely spaced lines, as you can see on this right image. If we process all that data through, we can now see how well the information from the full tensor gradiometer is able to interpolate the gravity field in between the survey lines. And you can see some of these salt bodies here are very well imaged, even though there isn't a survey line that actually goes across them. So these gradiometers are really fantastic for not only measuring the gravity field very accurately, but also for interpolating the gravity field in between the lines. And this is quite useful for a lot of surveys, because it means you can start off with a survey with a fairly wide line spacing. You can find the areas of geological interest quite quickly, and then you can go in and infill those areas with a tighter line spacing, which gives you the detail only where you need it. So it's really a way of optimizing the use of your survey instrumentation. Here's another geological model. This time it's of faults. Gravity gradiometry really is quite useful as well for finding faults in the subsurface. And that's because a fault has a fairly characteristic signature, because on one side of the fault you have high density rocks, and on the other side of the fault you have correspondingly low density rocks. On the throw side, these high density rocks have been pushed further down, and on this side they've been pushed further up. So across this fault boundary you get a high density contrast. And it's that density contrast which gives you a signal in gravity. And with the gravity gradient, you get a signal, as we see in this graph here. So seeing how that works in reality, this is a survey that we acquired earlier this year over an area absolutely full of faults, cross-cutting faults, and faults almost everywhere. And you can see on the left here, looking at the sort of theoretical fault signature in the gravity gradient field, you can see how that has appeared in many different locations in this actual survey data. And what we're able to do is tie in the data with any available 2D seismic data, and from that we can build very, very elaborate, very detailed and accurate 3D geological models. So one thing I've not talked about is various corrections on the data. Now, one of the most important corrections that we apply is known as the terrain correction. Now, when you're flying over an area where the topography has a reasonable amount of topographic relief, any gravimeter or gradiometer will be very sensitive to these lateral changes in density, where essentially you've got topography surrounded by air. So that's probably the most extreme density change that you'll ever encounter in one of these surveys is that interface between the topography and the surrounding air. And that will give a huge signal, and that's what you see in this blue trace on the top. So what we need to do is try to model that signal using measurements of the elevation of the terrain, and do a process what we call forward calculation to give us the response, the gravity response of that topography, and then remove that interference from the data. And after we've done that terrain correction, it leaves us with what we call the Bouyer gravity anomaly, or the Bouyer gravity gradient anomaly. And that's what you're seeing in this black trace here. So there's a severe decrease in the signal amplitude after doing this correction. And what we're left with now is a data set which more reflects the subsurface changes in density rather than the changes in density between the topography and the air. But when you've got a very accurate instrument like the enhanced FDG, which is measuring the gravity and gravity gradient fields with very high resolution and high accuracy, your final data is only as good as the corrections that you apply to it. So with a very, very sensitive instrument, that really does warrant a very, very accurate terrain correction. So this is the reason why we also acquire LiDAR data with our surveys. That gives us a very detailed image of the Earth's surface. It not only gives an image of the vegetation and all the buildings and those sort of things, but these LiDAR points are able to penetrate the vegetation and hit the ground and then reflect back to the aircraft. And so that gives us an image of the ground surface. And it's really the ground surface which is the important elevation model that we need for correcting the gravity data. So what we see on the left here is what's known as the digital surface model, the DSM, which includes all the trees, any buildings, any objects, as well as some ground points, which you can see in between the trees. But in the LiDAR processing that we do, we remove any points that have reflected from vegetation or buildings. And then we only use the points that have reflected from the ground, and that gives us what we know as the DTM, the digital terrain model. And it's this model which is used for the gravity terrain corrections. So I'll move on now to talking a bit more about the geothermal applications of airborne surveys, gravity gradiometry and gravity surveys. But first of all, just seeing how geothermal is sort of how gravity is being used in geothermal exploration. We'll look at a fairly simplistic model of a granite geothermal system. So this is based loosely on the Dartmoor outcropping granite here, which is sort of outlined by this blue polygon. And it's also taking inspiration from sort of generic hot rock geothermal, dry hot rock geothermal systems. And this diagram here sort of gives you a fairly typical model of what those granitic systems look like. So to see how gravity might help in this type of exploration program, or even sort of a drilling program, we need to construct a representative 3D geological model. And once we've got that geological model, we then assign the different densities to the different units in that model. And then we forward calculate the gravity from that model. And then we see how much useful information we might expect from a gravity survey. So here's a geological model. Like I said, it's loosely based on the Dartmoor outcropping granite. And this granite intrusion is modeled as a three-dimensional volume, and then it's placed within host geology. And these host this host geology is really consistent of a series of geological layers, and these will be sedimentary layers. There'll be metamorphic rocks surrounding the granite intrusion. To make the model more realistic, we add faults to the model. So these faults don't have necessarily any relevance to this area of Cornwall and Devon, but really they're just added to the model to make it more realistic. And then we assign the densities and we do forward calculations. So looking at this granitic pluton from underneath, this is what it looks like. And in terms of geothermal drilling programs, one of the challenges is really being able to model this contact between the granite and the associated host geology. And this is quite important because quite often it's preferable to drill in the associated host rock, because it's essentially easier to drill through that rock rather than through the granite, down to a suitable depth, and then hit the granite and then start drilling into the granite. And that's where the injection points are used in the geothermal, and then later on down the chain, the sort of production points to take out the hot fluids. So the challenge here is how well can gravity map that contact between the granitic intrusion and the host geology. So in this case, because the granite has a low density compared to the fairly old hard rocks which are hosting it, we expect a gravity low corresponding to the granitic pluton. So doing those forward calculations from this three-dimensional model really gives you an idea of what to expect from a gravity survey. Now, this, of course, could be a land survey, it could be an airborne survey, it could be a gradiometric survey. But this is what the gravity signature of that granitic pluton will look like. On the left here, we see the plane gravity, what we call the GZ, the Bouyer anomaly from this model. And there's a profile which is going from A to B, which is shown in this lower diagram here. So the blue line here corresponds to the gravity, and you can see, as we expected, we get a low corresponding to the granite. But of course, what we're interested in is how well can we map this area here, where it's potentially interesting for siting the geothermal drills. And that's very nicely highlighted if we do some transformations, mathematical transformations on this gravity signal. And the one transformation in particular that I'd like to show you today is this, what's called the total horizontal gradient. And this is basically just the total derivative of the gravity field on the left-hand side in both the X and the Y directions. And so those derivatives are just added together in quadrature, and that gives you what's known as the total horizontal gradient. And what that shows is it gives a very nice map of this region here, where you've got the outcropping granite shown as this inner solid white line, and you've got the edge of the granite, this sort of the widest part of the granite, which is highlighted by this black contour on the right-hand diagram. That's represented by this dashed white line in the middle image. And you can see the total horizontal gradient is given a very nice map of where this region, what I've called on the previous slide, the sort of drilling window, exists. So what this has shown is that gravity measurements can really help understand these granite intrusion geometries below the surface. And it's really, you really have to apply various transformations and filters to the data to bring out all the information that's possible from these gravity grids. Just looking at the gravity map in isolation, just the plain gravity, doesn't really show you all the detail, it doesn't highlight the features of interest. You really have to start applying some transformations and some essential interpretation. So there are other transformations that can be applied, and the other one I wanted to show you was a simple high-pass filter. So the high-pass filter removes the long wavelength trends in the gravity field and highlights the more short wavelengths, so the more things that are changing more abruptly. So you remember in the geological model, there was not only the granitic pluton, but there was also a lot of faults that were added to that model. And when we apply this high-pass filter to the gravity map, we see that it's very nicely highlighting the locations of these faults. And of course, the faults are also very important in terms of the geothermal projects. You want to be a target in the faults that are inside the granite to give you the necessary production, but also knowing the faults in the host rock in the surrounding area can be quite important as well. So I applied the same transforms to the BGS gravity data over Devon and Cornwall. And on the left-hand side, you see the plain Bouyer gravity map. And this is very nicely showing the lows in the gravity corresponding to the granitic intrusions. But then taking the horizontal derivative, the total horizontal derivative, we're seeing something very similar to what we were showing in the modeled response, where we have this high here, these contours, which are giving information about the outcropping surface and also the extent of that subsurface granitic volume. Applying the high-pass filter is highlighting faults in the various areas. There's a major fault running through here, which cross-cuts the granite. This is the Sticklepath fault. But I would say it's possibly pushing this data a little far, taking this high-pass filter, even though we've got very good coverage of the land data in this BGS compilation. To really get more information on the faults, it probably needs some extra data, more tightly spaced. Maybe an airborne survey would help in this case. So moving on to the land data in Northern Ireland, what we have in Northern Ireland is quite a nice coverage as well. There's slightly more than 11,000 stations. I think possibly more recently there's been some extra data added to this compilation. But a lot of this data originated from land surveys in the 1950s and 1960s, including some lake bottom surveys in 1983, but a huge campaign and compilation of many vintages of data that's gone into this. And it produces quite a nice Bouyer gravity anomaly map. And you can see several of the basins coming through there quite clearly, represented by the lows in the gravity, these blue areas. But what I'm going to use this data for is to see what an airborne gravity gradiometry survey might be able to add, or how would that compare to the land data. So I'm going to set up a simulation similar to what we were just looking at with the geological model, but this time using actual land gravity data. So the first thing to do is take that land data and apply a transformation that we call upward continuation, which raises the elevation of the data to what it would look like at airborne altitudes. Once we've got that data at airborne altitudes, we can then calculate again mathematically the gravity gradient field. So this is what the enhanced FDG would actually measure. So now we've got a set of signals which are representative of the gravity field over Northern Ireland at the airborne altitude, and also the signals that the EFDG would measure, the gradiometer. Now we sample these signals onto flight line plans, so we can test out different scenarios with different line spacing, and then we add the noise from the instrumentation to these signals, so we represent what the real measurements would look like. And then we process the data and do some simple gridding and assess the resultant gravity and gravity gradient maps. So just to show you the sort of preparation of the data, on the left we have the land gravity Bouyer anomaly. And then after applying what we call the upward continue and the first vertical derivative, we've transformed that data into airborne data and also the gravity gradient components. And the GZZ component is what you see on the right-hand image here. So now we've got the signal that would be measured by the airborne system. We can now run a few simulations. So the first scenario is an airborne survey with a very wide line spacing. In this case, I've chosen 16-kilometer line spacing and 40-kilometer tie line spacing. And we can see after processing this data and producing a gravity map, what that would look like. On the left-hand image, you can see the gravity, the Bouyer gravity map seems to hang together quite well. We can see these basins coming through quite clearly. But if we look at the gravity gradient map, which is in many ways a high resolution version of the gravity map, we can see we've lost a lot of the trends. The data is just too widely spaced to give a good sampling of the full gravity gradient field of this area. Now, of course, this is a very wide line spacing survey, and I've estimated with the enhanced FDG, this would take about 3 days to acquire. So just after 3 days, you would get a reasonably nice gravity map. Wouldn't really hang together in terms of all of the details that come through in the gravity gradient maps, but nevertheless, it's quite useful even after 3 days. So if we now go to half the line spacing, so we've got a line spacing of 8 kilometers now. So these are the flight lines going east-west, and we've got half the tie line spacing. So now we're down at 20 kilometers. So the tie lines are the north-south lines. The gravity field is now looking more high resolution. We've got a lot more detail in there. And the gravity gradient map is now really showing the trends in the data. And this survey takes about, I've estimated, 5 days and a total of roughly 5,000 kilometers. By the way, the numbers here I'm quoting are for the entire survey over this area, not just the survey over the data that we can see. So now we halve the line spacing again. So we're at 4-kilometer line spacing and 10-kilometer tie line spacing. And I would say at this point, we're really representing what we can see in the land data quite accurately. And this survey, I've estimated, would take about 10 days of flying. One more, this is going now to a 2-kilometer line spacing and a 5-kilometer tie line spacing. I think this is now very, very equivalent to the land data and may even be sampling slightly higher data. If there was signals of higher frequencies in this simulation, I think these would start coming out in this scenario. So as a conclusion, I would say that the land data that's available over Northern Ireland could have been acquired to result in a similar resolution from an airborne EFDG survey measuring the gravity gradients with a line spacing of about 4 by 10 kilometers. And this would take around 10 days of flying, but would also, of course, give the gravity gradient and gravity map over this entire area. So it really goes to show how efficient some of these airborne surveys can be, in the sense that they can cover these areas very, very quickly, certainly relative to the long durations, the many months and years of land gravity campaigns that have gone into building up this compilation of gravity stations. So I'd like to finish there. So I hope I've given some details about how gravity measurements can help solve many geological challenges. And the answer for dynamic measurements from the air is really gravity gradiometry. And the reason there is that they can cope with the vibrations in the aircraft, but they can survey large areas very quickly, both onshore and offshore, and give you good coverage within days rather than years compared to land data. And we're seeing that airborne surveys are already playing quite an important role in geothermal exploration.